Reality may be built from tiny, indivisible pixels. This is not science fiction, but a serious theory in modern physics called the quantum nature of space-time. It proposes that the smooth, continuous universe we perceive is an illusion, emerging from a fundamental graininess at the smallest possible scale. By the end of this journey, you will understand how this single idea could solve the greatest mysteries of the cosmos, from the heart of black holes to the origin of the Big Bang. How can a universe of finite pieces appear so seamless? What would it mean if time itself was not a continuous flow, but a series of quantum ticks? How much of what we consider real is just a high-resolution approximation? What does it feel like to question the very fabric of your existence? For centuries, the greatest minds in physics painted our universe as perfectly smooth. Isaac Newton's calculus and Albert Einstein's theory of general relativity both described a reality where space and time were infinitely divisible. You could always find a smaller point between two others, a shorter moment between two ticks of a clock. This was the classical view, an elegant and seamless canvas where everything flowed without a single visible brushstroke. It was a vision of absolute continuity, and it worked brilliantly, predicting the orbits of planets and the bending of starlight with stunning accuracy. But this beautiful picture had hidden cracks. Within the majestic equations of Einstein, certain situations led to nonsensical answers, to infinities of density and curvature that signaled a complete breakdown of physics. These were the paradoxes lurking in the heart of black holes and at the instant of the Big Bang. The very tools that described a smooth universe were pointing to their own limitations, whispering that the canvas itself might be an illusion. The tremendous success of these continuous models had, ironically, masked a fundamental incompleteness. The puzzle of these infinities demanded a solution far more radical than anyone had ever considered, setting the stage for a revolution that would question the very fabric of reality. This breakdown of smoothness becomes inevitable when we look closely enough. Think about a digital photograph on your screen. From a normal distance, the image appears seamless, a perfect portrait of reality. But zoom in far enough and the illusion shatters. You see the individual pixels, the tiny squares of color that form the entire picture. Our universe might operate on a similar principle. There is a fundamental limit to how close you can zoom into the fabric of reality, a smallest possible distance known as the Planck length. This is not just small, it is inconceivably tiny. If you enlarged a single atom to the size of the entire observable universe, the Planck length would be roughly the height of a single tree. At this scale, the serene, continuous canvas of Einstein's universe is expected to dissolve into a turbulent quantum foam. Picture the surface of a pond on a windy day. From the shore, it looks like a single, shimmering sheet, but kneel down and look at the surface itself, and you see a chaotic dance of countless water molecules, constantly bumping and jostling. The smooth surface was only an average, a large-scale effect of a microscopic frenzy. In the same way, what we perceive as empty, smooth space-time may be a seething ocean of quantum fluctuations at the Planck scale. Virtual particles pop in and out of existence, and the geometry of space itself writhes and twists. This means the idea of a precise location, a mathematical point in space, is a fiction. It is a convenient approximation that works perfectly in our everyday world, but breaks down completely at the universe's most fundamental level. There is no such thing as an exact here or a perfect now in this granular reality. We are forced to confront a profound truth that the continuous reality we experience is an emergent property, a high-resolution projection from a pixelated source code. So what does this fundamental graininess actually look like, and how could we ever hope to see it? This granularity of spacetime leads to an even more radical idea. The very geometry of our universe, the way we measure distances and angles, might not be continuous either. It could be quantized. Think of an atom with its electrons occupying only specific, allowed energy levels. An electron cannot exist between these levels. It must jump from one to another in a quantum leap. In a pixelated universe, the same principle applies to space itself. There would be a smallest possible area, a smallest possible volume, beyond which the concept of making something smaller becomes meaningless. You cannot have half a pixel of spacetime. This means that the smooth curves and surfaces of Einstein's universe are, at the most fundamental level, an approximation. The cosmos is not a perfectly polished sphere, but a vast, intricate mosaic. Each tile in this mosaic is an atom of space, and together they weave the fabric of reality we perceive. This quantization is not just a mathematical quirk, it is a direct solution to the devastating infinities that appear when we try to combine general relativity with quantum mechanics. Those infinite densities at the center of black holes, those nonsensical singularities, they arise from the assumption that space can be divided forever. But if there is a smallest possible volume, then density can only become so high. It hits a ceiling. The math simply cannot produce an infinity when the building blocks themselves are finite. This single, elegant idea of a pixelated geometry offers a clear path out of the theoretical wilderness, pointing the way toward a complete theory of quantum gravity. But if space itself is made of discrete pieces, what does that imply for the flow of time? This ultimate pixel of reality has a name: the Planck length. It is a number so small it defies human intuition, approximately 10 to the negative 35th meters. To say it is a billion times smaller than a proton is still a dramatic understatement. This is the scale where the smooth fabric of spacetime is expected to dissolve into a quantum foam, where gravity itself must be understood through the lens of quantum mechanics. It is the universe's native resolution, the absolute limit of how finely we can zoom into the cosmic picture. The sheer smallness of this scale is almost impossible to visualize, but one analogy can help us grasp its staggering proportions. If you were to magnify a single atom to the size of our entire observable universe, the Planck length at that immense scale would be roughly the height of an average tree on Earth. In that cosmic expanse, the fundamental building block of everything would be no larger than a tree. This is not merely small, it is the final frontier of smallness, the end of the line for the concept of distance itself. At this ultimate resolution, our everyday logic begins to break down. The very ideas of here and there, or before and after, start to blur and lose their familiar meaning. You cannot have a location smaller than a single pixel, so the idea of moving continuously from one point to an adjacent one becomes meaningless. There is only here and then there, with nothing in between. In this realm, the universe operates not on certainty, but on a fog of pure potentiality, a seething ocean of probabilities where geometry itself flickers in and out of existence. If this is the fundamental grain of space, then what kind of cosmic clock could possibly tick in sync with such a microscopic grid? One of the most compelling visions for this pixelated cosmos is known as loop quantum gravity. This theory takes the idea of a granular universe and weaves it into a breathtaking new picture. It proposes that space itself is not a silent, empty stage upon which events unfold. Instead, it is a dynamic, vibrating web of relationships. The fundamental building blocks are not points, but tiny, one-dimensional loops. Think of each loop as an elementary thread of reality, carrying a smallest possible unit of area. These loops do not exist in space, they connect with one another to form space. Their interweaving creates a vast, ever-changing structure called a spin network. This is the cosmic tapestry, a glittering web of quantum connections where each knot and thread defines the geometry of a region. The smooth, curved space of Einstein's equations emerges as a kind of average, a large-scale effect of this microscopic network's intricate pattern. And what of time? In this radical view, time does not flow as a river. It emerges tick by tick from the evolution of this network. Each change in the connections, a rearrangement of the cosmic weave, constitutes a single quantum step forward. This framework finally gives us a concrete, mathematical image of a universe built from finite pieces. The seamless continuum we have always taken for granted is revealed as a magnificent illusion, a high-resolution projection from a fundamentally discrete source code. But if our reality is woven from such a quantum fabric, how could we ever find proof of its existence? While loop quantum gravity weaves space from threads, another profound theory paints an even more surreal picture. String theory gives us the holographic principle, an idea so counterintuitive it seems to rewrite the rules of reality itself. Imagine the security hologram on your credit card. It appears as a full, three-dimensional object hovering in space, yet all of its information is stored on the flat, two-dimensional surface of the card. The holographic principle applies this same logic to the entire cosmos. It suggests that all the information describing everything within a volume of space, every star, every planet, every person, could be perfectly encoded on the boundary enclosing that volume. For our universe, this would mean that the rich, three-dimensional reality we experience, with all its depth and substance, might be a magnificent projection from a vast, two-dimensional information layer at the cosmic edge. Think of it as the universe having a skin, an immense spherical film where the ultimate data of existence is stored. The world we see and feel is not the primary reality, but a holographic readout of that data. This completely inverts our understanding of dimension. We perceive ourselves living inside a three-dimensional volume, but the true, fundamental description of our universe might be written on a distant, two-dimensional screen. This has a direct and startling consequence for the pixelation of spacetime. The fundamental grains, the pixels of reality, may not be scattered throughout the space we occupy. Instead, they are packed onto that two-dimensional boundary. Our three-dimensional world, with all its complexity, emerges from the interplay of these incredibly dense bits of information on the cosmic surface. Each pixel on the boundary does not correspond to a single point in our space, but to an entire region. It is as if the entire content of a room is not defined by points within the room, but by the intricate patterns painted on its walls. This resolves a deep paradox about black holes, where the amount of information a volume can hold is limited not by its volume, but by the area of its surface. The universe itself seems to be obeying this holographic law, forcing us to ask a truly unsettling question. Is the solidity of the world around us, the very feeling of depth, merely an elaborate and convincing illusion? But this pixelated reality presents us with a paradox far stranger than space itself. The very flow of time, something we feel with every heartbeat, faces a profound crisis in the quantum realm. In a universe woven from a spin network, there is no background clock ticking away for everyone and everything. There is no universal now, no cosmic second hand sweeping across the heavens. Instead, time is a ghost. It emerges only from the relationships between events within the quantum tapestry. Each change in the network, each rearrangement of a loop, defines a single quantum step. One change happens and then another, and this sequence of changes is all that time truly is. The smooth, flowing river of time we experience is an illusion, a large-scale consequence of countless microscopic ticks in the geometry of space. This forces us to abandon the Newtonian idea of a master clock for the universe. Nothing is fundamentally ticking. What we perceive as the relentless march of time is just the universe comparing one state of itself to a previous state. Your watch doesn't measure time, it correlates its own internal changes with the changes happening in the world around it. So what does this mean for our most basic experiences? The feeling that the past is fixed and the future is open might itself be a kind of projection, a story our brains tell us to make sense of this underlying, timeless churn of quantum relationships. If time is not a fundamental ingredient, then what does that say about the reality of change, or even the reality of our own memories? So how do we search for evidence of a reality we cannot directly see? The challenge is immense, like trying to discern the individual grains of sand on a beach while viewing it from an airplane. We cannot build a microscope powerful enough to peer down to the Planck length. Instead, scientists must become cosmic detectives, looking for subtle clues this granular structure imprints on the universe around us. One promising clue involves the ancient light from catastrophic explosions known as gamma-ray bursts. These are the most energetic events since the Big Bang, and their light travels across billions of years to reach us. Think of this light not as a smooth wave, but as a torrent of the tiniest possible particles, photons, each with a different energy. Now, if spacetime were perfectly smooth like a freshly paved highway, all these photons, regardless of their energy, would arrive at the same time after their long journey. But if the universe is pixelated, the journey changes. The fabric of space would have a subtle texture, like a road made of cobblestones. A high-energy photon, vibrating more rapidly, might interact with this granular texture differently than a lower-energy one. It could experience a tiny, almost imperceptible delay. Over a journey of billions of light years, that minuscule delay could add up to a measurable difference in their arrival times. Our most powerful telescopes are now searching for this exact signature, looking for a faint whisper of graininess in the most powerful screams from the cosmos. Another experiment is happening much closer to home, inside laboratories with some of the most precise clocks ever built. These atomic clocks are so accurate they would not lose a second in billions of years. Their steady tick is the most reliable rhythm we know, but if spacetime is a quantum foam churning and bubbling at the smallest scales, even this perfect rhythm might be disturbed. The idea is that the foam would cause tiny, random fluctuations in the very geometry of space around the clock. This would make the clock's ticking rate jitter slightly, like a metronome placed on a trembling surface. By comparing two of these ultra-precise clocks, scientists hope to detect this faint tremor, a shiver in time itself that betrays the restless, pixelated nature of the reality beneath our feet. These are not flights of fancy, but concrete experiments hunting for the ghostly fingerprints of a grainy universe. They force us to ask what other profound illusions shape our experience of the world. Black holes are cosmic pressure cookers, forcing the deepest secrets of reality to the surface. Their immense gravitational pull doesn't just bend space-time, it twists it into a knot where our current laws of physics simply unravel. At the edge of a black hole, at the point of no return known as the event horizon, the smooth fabric described by Einstein meets the chaotic uncertainty of the quantum world. This boundary is where our universe's most profound puzzle plays out. It was Stephen Hawking who first realized that black holes are not entirely black. In a stunning revelation, he showed that they slowly leak radiation, glowing with a faint heat. They evaporate, fading away over cosmic eons. This Hawking radiation was a monumental discovery, but it created a crisis. Where does this heat come from? According to general relativity, nothing, not even information, can escape a black hole's grip. Yet quantum mechanics insists that information about what fell in can never be truly destroyed. So when the black hole evaporates, what happens to all the data of the stars, planets, and atoms that were consumed? This is the infamous black hole information paradox, a direct conflict between our two most powerful descriptions of reality. The solution likely lies in the quantum nature of the event horizon itself. If space-time is pixelated, then the horizon is not a perfectly smooth, two-dimensional membrane. It must be a seething, vibrating surface built from a tapestry of microscopic quantum grains. Each grain could store a single bit of information, like an ultimate pixel on the cosmic screen. The information of what falls in isn't lost behind the horizon, but is perhaps smeared and encoded across this frenetic quantum surface, only to be slowly radiated back out, scrambled in the Hawking glow. In this view, a black hole is not a destructive pit, but a transformative processor. It takes the complex three-dimensional information of an object and translates it onto a two-dimensional quantum surface, a perfect demonstration of the holographic principle in action. The key to resolving the paradox and to finally uniting gravity with the quantum world might be hidden in the pixelated code of these dark objects. If we can decipher how a black hole stores and processes information, we will have taken a monumental step toward reading the universe's own source code. What other cosmic illusions might we uncover once we learn to see this code in action? The smoothness of space-time is an illusion that solves one problem, but it creates another of staggering proportions. This is the cosmological constant problem, a puzzle so profound it makes the infinities in black holes seem almost simple. Quantum field theory, our most successful framework for describing particles and forces, tells us that empty space is not empty at all. It is a seething ocean of virtual particles, constantly flickering in and out of existence. This quantum frenzy should fill the vacuum with an immense energy, a pressure that would cause the universe to expand at a rate so furious that galaxies, stars, and planets could never have formed. The math predicts a value for this vacuum energy, this dark energy that is absurdly large. Yet when we look at the cosmos, we measure a value for dark energy that is almost zero. It is there just enough to accelerate the expansion of the universe, but it is 120 orders of magnitude smaller than the prediction. To write out that number, you would need a 1 followed by 120 zeros. This is not just a small error, it is the most glaring discrepancy in all of science, a screaming contradiction between our theory of the small and our observation of the large. How can the vacuum be so busy yet so quiet? A pixelated cosmos might hold the key. The catastrophe of the cosmological constant arises from the assumption that we can sum up the energy of these quantum fluctuations across an infinitely divisible space. There is no limit to how finely we can slice the vacuum, so the energy just keeps adding up to an astronomical figure. But what if you cannot slice space forever? This is where the fundamental graininess of reality changes everything. If there is a smallest possible volume, a single pixel of space-time, then there is a natural cutoff. You cannot probe scales smaller than the Planck length, so you cannot sum up energy from scales that do not exist. It is like trying to count the waves in the ocean. You could count every large wave and every tiny ripple, but you would not count the jostling of individual water molecules. That is a different level of reality altogether. In a pixelated universe, the frantic quantum jitter is the jostling of the molecules. The smooth, large-scale vacuum we experience is the calm surface of the ocean. The discrete structure of space itself might act as a built-in regulator, cancelling out almost all of the vacuum energy through the specific way its geometry vibrates and interacts. The tiny leftover value we observe as dark energy could be the residual hum of this quantum cancellation, a faint echo of the universe's granular heart. This means the ultimate fate of our cosmos, whether it expands forever or eventually contracts, is not determined by some mysterious force, but is intrinsically linked to the tiniest possible structures within it. The largest questions we can ask are written in the language of the very smallest things that exist. This radical simplification brings us to Causal Set Theory, a vision of reality built from almost nothing. Where other theories weave space from loops or project it from holograms, Causal Set Theory proposes that the universe is, at its heart, a vast collection of events. Each event is a simple, structureless point. These points are not laid out in a pre-existing space, and they do not tick in a pre-existing time. The only thing that defines them is a single, fundamental relationship. One point either comes before another, or it does not. This relationship, this raw sequence of cause and effect, is the universe's entire foundation. Imagine a billion scattered grains of sand, with an invisible arrow drawn from one grain to another, only if the first could possibly influence the second. The sand has no texture, the grains have no size, and there is no space between them. All that exists is the network of arrows, the pure order of what leads to what. From this immense, intricate web of causality, the illusion of a continuous, four-dimensional spacetime is thought to emerge. The smooth geometry we measure with our clocks and rulers is not fundamental. It is a large-scale, approximate picture, much like a smooth curve drawn by connecting a series of discrete dots on a graph. The curve appears continuous, but its true nature is a sequence of individual points. In this view, the solidity of a rock and the flow of a river are not primary realities. They are secondary patterns that arise from the deep, underlying sequence of cosmic events. What we perceive as a continuous world is really a dense cascade of causes and their effects, a story written in the most minimal language possible, the simple language of before and after. A profound symmetry lies at the heart of Einstein's universe, the principle of Lorentz invariance. It states that the laws of physics are the same for everyone, whether you are standing still or moving at a constant velocity. The speed of light is the ultimate speed limit, a constant that remains the same for all observers. This symmetry is the bedrock of modern physics, the reason why your experience of reality remains consistent no matter how you move through space. But a pixelated cosmos threatens to shatter this sacred foundation. If spacetime has a fundamental grain, a smallest possible size, then it could act like the underlying grid of a digital photograph. A digital image has a preferred orientation defined by the rows and columns of its pixels. If you rotate the image, you can see the jagged edges of the pixels along the diagonal lines. In the same way, a granular universe might have a hidden grid, a preferred frame of reference against which all motion is measured. An observer moving relative to this grid might measure tiny, subtle differences in the laws of physics, especially in the speed of light itself. This is the specter of Lorentz invariance violation. It suggests that the perfect cosmic democracy of Einstein's theory, where no frame of reference is special, might be an approximation that breaks down at the universe's most fundamental resolution. Scientists are hunting for this violation by studying the most ancient and energetic light in the universe, from gamma-ray bursts and distant quasars. They are searching for a telltale sign that higher energy photons, vibrating more rapidly, are interacting with the cosmic grid and arriving a fraction of a second later than their lower energy counterparts. Finding even the faintest such delay would be like discovering the universal pixel structure, forcing a complete rewrite of our understanding of space, time, and motion. It would prove that the seamless, symmetric cosmos we thought we inhabited is a magnificent and convincing facade. This quantum foam is a direct consequence of the universe's inherent uncertainty. The Heisenberg uncertainty principle tells us that we cannot precisely know both the energy of a system and the exact time of its measurement. This trade-off is not a limitation of our instruments, but a fundamental property of reality itself. At the scale of the Planck length, this uncertainty applies to the fabric of spacetime. For unimaginably brief moments, vast amounts of energy can be borrowed from nothing, warping geometry in extreme and violent ways. The result is not a calm, empty void, but a turbulent sea where the very concepts of here and there lose their meaning. In this foam, virtual black holes wink into existence, their gravitational pull so intense that not even light could escape, only to vanish a moment later. Wormholes, those fabled cosmic shortcuts, are theorized to constantly form, connecting two distant points in space before pinching off into nothingness. Think of the surface of a carbonated drink, a chaotic fizz of bubbles constantly forming, merging, and popping. Now, imagine that each bubble is a momentary tunnel through the geometry of space itself. This is not a passive background. In a truly pixelated cosmos, this foam is the primary texture of reality. The smooth, classical space of planets and stars is the calm, average surface of this deeper, frantic ocean. These fleeting wormholes present a staggering possibility. If they could be stabilized or harnessed, they would render our conventional understanding of distance completely obsolete. A journey across the galaxy, which would take light tens of thousands of years, could theoretically be instantaneous through the right microscopic tunnel in the foam. The entire cosmos might be connected by a hidden, subatomic web of transient bridges, a quantum underground that makes a mockery of the vast emptiness we see between the stars. The immense distances that isolate celestial islands could be an illusion, with everything secretly knotted together in a hyper-connected whole. This leads us to the most staggering possibility of all, that space-time is not the foundation of reality, but a consequence of it. Our continuous four-dimensional universe may be a grand collective illusion. Think of the temperature of a gas. A single molecule flying through the air does not have a temperature. Temperature is not a property of the individual, but a statistical average that only makes sense when you have a vast, chaotic collection of molecules. Their combined frantic motion gives rise to this new, emergent property we call heat. In the very same way, the smooth, geometric stage of spacetime may not be a fundamental ingredient. It could be a large-scale effect, a kind of cosmic temperature that emerges from the interactions of countless, more basic entities. These are the loops of loop quantum gravity, the vibrating strings of string theory, or the pure quantum bits of information in the holographic principle. These fundamental building blocks do not exist within space and time. They are not little objects sitting in a container. Instead, their relationships, their interactions, and their intricate weaving create the container itself. They generate the very notions of here and there, of before and after, from a realm that is utterly alien to such concepts. This underlying quantum system operates in a domain beyond space and time as we know them. It is a world of pure information, of pure potentiality, where the logic of cause and effect may not even apply in a familiar way. From this frenetic, non-spatiotemporal dance, the serene continuity of our world condenses, much like a smooth wave emerges from the chaotic collisions of trillions of water molecules. The solid ground beneath your feet, the vast emptiness between stars, and the relentless flow of time, all of it could be a magnificent and convincing mirage. If this is true, then we are not merely living in the universe, we are a temporary pattern woven from its deepest, most mind-bending code. This transforms our understanding of reality from one of substance to one of pure data. In the information theoretic viewpoint, the universe is not fundamentally composed of tiny billiard balls or ethereal fields, but of bits. Each of those pixels of spacetime we have been discussing could be thought of as a qubit, a fundamental unit of quantum information. A qubit is not like a simple 0 or 1 in a classical computer. It is a quantum bit capable of existing in a state of superposition, representing both 0 and 1 simultaneously. This is the same strange principle that allows quantum computers to perform calculations in parallel universes of possibility. Now, imagine the entire cosmos as a processor. The dynamics of the universe, the evolution of galaxies, the formation of stars, and the beating of your own heart would then be a computation. It is a cosmic quantum computer, unimaginably vast, processing these qubits according to a specific, underlying set of rules. In this radical picture, the laws of physics as we know them, from gravity to electromagnetism, are not fundamental truths etched into the cosmos. They are the software, the elegant and efficient code that runs on the hardware of pixelated spacetime. This is not a metaphor. It is a serious proposal that elegantly bridges the worlds of theoretical physics and computer science. It suggests that existence, at its most fundamental level, is a vast and complex information processing system. What we perceive as the flow of time is simply the processing of these cosmic bits. What we feel as the force of gravity could be an emergent phenomenon, a consequence of the way information is entangled and shared across the network. The solidity of matter itself might be a kind of data structure, a stable pattern in the universal computation. This forces a deeply philosophical question. If we are all patterns of information being processed on a cosmic scale, then what does that make our consciousness, our memories, our very sense of being? Are we, too, just exceptionally complex and self-aware algorithms running on the hardware of a quantum universe? The quiet hum of the cosmos has finally become audible. We are no longer limited to observing the universe with light alone. We can now listen to the vibrations of spacetime itself through gravitational waves. These are not waves that travel through space, but actual ripples in the very fabric of geometry, generated by the most violent events in existence, like the collision of black holes. As these waves propagate across billions of light years, they carry with them a pristine imprint of spacetime's true nature. If the fabric of reality is smooth, the waves will travel undisturbed. But if it is pixelated, if it possesses that subtle granular texture, the journey will leave a mark. Think of the way light shimmers as it passes through the hot air rising from an asphalt road. The air's uneven density distorts the light's path. In a similar, far more subtle way, a grainy spacetime could leave a faint fingerprint on a gravitational wave, perhaps by slightly altering its polarization, the specific way it twists and contorts space as it passes, or its phase, the rhythm of its peaks and troughs. Our current ground-based detectors are marvels of engineering, but they are like listening to a symphony with your head underwater. The finest details are lost in the cosmic noise. The next generation of observatories will change everything. Imagine a constellation of 3 spacecraft, flying in a perfect triangle millions of kilometers on each side, connected by lasers. This is the Laser Interferometer Space Antenna, or LISA. Isolated from the seismic rumble of Earth, this instrument will be so exquisitely sensitive it could detect a change in distance smaller than a single atom across that immense span. It will be able to hear the gravitational hum of countless binary systems, the low-frequency ripples from the mergers of supermassive black holes, and in that pristine data, scientists will search for the ghostly signature of spacetime's fundamental grain. Catching a single gravitational wave and finding this tiny distortion would be more than just another discovery. It would be a direct message from the foundation of reality, an empirical whisper confirming that the universe is not a continuous whole, but is woven from finite quantum threads. This would transform our philosophical understanding of existence from an abstract debate into a measurable fact, forcing us to accept that the seamless stage upon which our lives play out is, in truth, a magnificent and intricate quantum mosaic. This granular foundation of reality does more than just reshape physics. It shatters our deepest philosophical certainties. For over 2 millennia, Zeno of Elea presented a paradox that seemed to prove motion was an illusion. To walk from one side of a room to the other, he argued, you must first cover half the distance, then half of the remaining half, and so on, creating an infinite number of steps to complete a finite journey. Since no one can complete an infinite number of tasks, motion must be impossible. We know we move, so the paradox was a puzzle, a flaw in our reasoning about continuity. A pixelated cosmos provides the stunningly simple solution. You cannot divide the path forever. There is a final, indivisible step, a single quantum of space that you cross in a single quantum of time. The infinite regress of have simply stops at the universe's native resolution. Motion is not a smooth glide, but a rapid succession of quantum leaps from one location to an adjacent one, with nothing in between. The paradox dissolves because the fundamental nature of the journey is not continuous but discrete. This digital underpinning forces us to re-examine the ancient debate of free will versus determinism. If the universe truly computes its future from a finite set of discrete states, like a cosmic computer processing a sequence of instructions, does that mean every future state is already determined by the current one? Is our feeling of making a genuine choice just an illusion, a predictable output of an unimaginably complex calculation? Or does the inherent randomness of quantum mechanics, the dice rolls at the heart of every pixel, inject genuine novelty and openness into the cosmic program? Perhaps our wills operate within the probabilities defined by this quantum computation, making our choices neither fully predetermined nor entirely random, but a unique product of a universe that calculates its way through possibility. A more intimate question then arises. If our reality is digital, is it somehow less real? Does the discovery that the Mona Lisa is made of discrete daubs of paint make it less of a masterpiece, or does it reveal the profound technique behind its creation? The pixelation of spacetime does not suggest our world is a simulation in the sense of a human-made construct. Instead, it points to a universe whose very essence is mathematical and computational. The solidity, the warmth, the pain and joy we experience are no less real for emerging from a deeper, discrete code. They are the magnificent, high-definition output of that code. The love a parent feels for a child is not diminished by the fact that the brain processing that emotion operates on neuronal firings, which themselves rely on quantum chemistry, rooted in the exchange of fundamental particles, which are perhaps at the very bottom, excitations in a space-time tapestry woven from bits. The reality of the experience is in its meaning and its impact, not in the substrate. This shifts the philosophical quest from asking what the universe is made of to asking what kind of information it processes and what story that computation is telling. We are left not with a colder, more mechanical universe, but with a far more mysterious and elegant one, where the deepest truths of existence are written in a language of ultimate simplicity, waiting to be read. The solid ground beneath our feet holds a secret blueprint for the cosmos. We can find clues about the quantum structure of space-time not only by looking up at the heavens, but by looking down at the strange behavior of matter right here on Earth. A remarkable bridge has been built between the physics of the impossibly large and the physics of the incredibly small, and it runs straight through the heart of an ordinary pencil. The graphite in a pencil tip contains layers of carbon atoms arranged in a hexagonal lattice, a material known as graphene. When you isolate a single layer of these atoms, something extraordinary happens. The electrons moving through this chicken wire grid do not behave like normal particles. Their motion is governed by equations that are mathematically identical to the equations describing how light particles, or photons, move in a curved spacetime, like that around a black hole. This is not a vague similarity, it is a precise mathematical parallel. The graphene lattice, with its discrete, pixel-like array of carbon atoms, creates an environment where the electrons act as if they are living in a universe with its own unique geometry, a geometry that emerges entirely from the pattern of the atomic grid. This discovery gave birth to the field of analog gravity, where tabletop experiments can simulate some of the most extreme phenomena in the universe. In certain laboratory systems, like supercold fluids or specialized crystals, physicists can create a flow so swift that ripples within the fluid, the equivalent of light particles, cannot escape. This creates an effective event horizon, an artificial black hole in a beaker. By studying how these ripples behave at this man-made horizon, we can test ideas about how Hawking radiation might be generated, probing the quantum effects of gravity without ever needing to visit a real black hole. The true power of this analogy lies in its illustration of emergence. In a crystal, the smooth, wave-like behavior of an electron is an illusion. The electron is not a wave sliding through a continuous medium. It is hopping from one discrete atomic site to the next. Its elegant, continuous motion is an average, a large-scale consequence of the underlying pixelated lattice. In exactly the same way, the smooth, curved spacetime of our universe could be an emergent property, a large-scale consequence of an underlying quantum network we cannot yet see. The continuous stage upon which reality plays out may be a collective behavior, a kind of cosmic vibration arising from the interconnected hum of countless fundamental grains. By understanding how a seamless reality emerges from a discrete grid in a simple piece of carbon, we gain the intuition to believe that the entire cosmos might be built the same way. The very fabric of space may be woven from a ghostly quantum thread. That thread is entanglement, the mysterious connection Einstein famously called spooky action at a distance. When two particles become entangled, they lose their individual identities, becoming a single, unified quantum system. No matter how far apart they travel, a measurement on one instantly influences the other, a connection that seems to defy the speed of light. For decades, this was seen as a bizarre quirk of the small scale, with no real bearing on the large-scale structure of the cosmos. But a revolutionary idea is turning that view on its head. The glue holding the smooth, continuous stage of spacetime together might be quantum entanglement itself. This is the heart of the ER equals EPR conjecture, a proposal that unites two of Einstein's most radical ideas. One, EPR, is the entanglement paradox that he thought exposed the absurdity of quantum mechanics. The other, ER, refers to the Einstein-Rosen bridge, a theoretical tunnel through spacetime now popularly known as a wormhole. The conjecture boldly states that these are not two different things, but two sides of the same coin. Two particles that are quantum entangled are not communicating faster than light across a vast emptiness. They are, in fact, connected by a microscopic wormhole. The vast distance between them is an illusion. bridged by a tiny, subatomic shortcut in the geometry of reality. In a universe built from a pixelated spin network, this idea becomes profoundly concrete. The connectivity of that network, the way its loops and threads are woven together, could be a direct map of the entanglement between different regions. Each quantum of space is entangled with its neighbors, and this web of mutual information is what creates the geometry we perceive as distance and proximity. The more entangled two regions are, the closer they are in space. If you could somehow cut all the entanglement between two areas, the space between them would literally tear apart. This suggests a staggering new foundation for reality. Space is not a primary, empty container. It is an emergent property of a quantum internet, a network of informational links. The pixelation of spacetime is then a direct reflection of the discrete, quantized nature of these connections. Each pixel is not an isolated block, but a knot in a vast web of relationships. The solidity of the world around us is the result of an unimaginably dense tapestry of these quantum handshakes, constantly reaffirming the geometry of here and there. So the next time you place an object on a table, consider this. The table holds the object up not just through the force of its atoms, but through the silent, ceaseless hum of entanglement that binds its pixels of space together, weaving the very stage upon which the object can rest. Yet the idea of a pixelated cosmos is not the only path forward. A rival vision, known as asymptotically safe gravity, proposes a universe that remains perfectly smooth and continuous, even at the most extreme scales. In this framework, the force of gravity itself is not a constant, but a shape-shifting entity. Its strength depends entirely on the energy scale at which you measure it. At the low energies of our everyday world, gravity is the familiar, weak force we experience. But as you probe to higher and higher energies, approaching the Planck scale, the strength of gravity is predicted to change in a very precise mathematical way, reaching a fixed point where it becomes well-behaved and finite. This elegant dance allows the theory to tame the destructive infinities that normally appear when merging gravity with quantum mechanics, all without ever needing to chop space and time into discrete pieces. It is a universe that remains an infinitely divisible whole, a seamless continuum from the largest galaxy to the smallest conceivable distance. This creates a fascinating and productive tension in theoretical physics. We have two fundamentally different paradigms vying for the title of ultimate reality. On one side, the discrete, pixelated models like loop quantum gravity, where space and time emerge from a quantum network. On the other, continuous theories like asymptotic safety, which preserve the classic smoothness of Einstein's spacetime. This competition is the engine of scientific discovery. Each camp is forced to sharpen its ideas, to refine its mathematics, and most importantly, to make specific, testable predictions that distinguish it from the other. The existence of spacetime pixels is one such definitive prediction. A confirmed detection of graininess, perhaps in the jitter of an atomic clock or the distorted polarization of a gravitational wave, would be a monumental blow to any theory that requires perfect continuity. It would instantly rule out an entire class of alternatives, narrowing the path toward a final theory of quantum gravity. The universe, in its silent way, is waiting to cast the deciding vote in this grand debate, forcing us to ask which is the more profound truth, an infinitely smooth canvas or a breathtaking cosmic mosaic built from finite grains. This mathematical fuzziness finds its purest expression in a concept known as non-commutative geometry. In our familiar world, pinpointing a location is straightforward. If you are told to find a treasure buried 5 steps east and then 3 steps north, you will arrive at the exact same spot as if you were told to go 3 steps north first and then 5 steps east. The order of your movements does not matter, the coordinates commute, but what if, at the universe's most fundamental level, this simple rule broke down? Non-commutative geometry proposes exactly that. In this framework, the very coordinates of spacetime cease to commute. The act of measuring position in one direction interferes with the measurement in another. It would be as if measuring east-west and north-south were like the quantum spin of an electron, where checking one property fundamentally disturbs the other. The mathematical expression for this is beautifully simple: x, y does not equal 0. This tiny, elegant equation carries a revolutionary meaning. It tells us that there is no such thing as a perfect mathematical point in this primordial reality. You cannot specify an exact here with infinite precision. Instead, every location is inherently fuzzy, a kind of quantum blob or a smeared-out probability. This is not a blurring due to poor measurement, but a fundamental property of the universe itself. The void is filled with a natural graininess that prevents us from ever zooming in to a true singularity. It is as if the universe has a built-in resolution limit, not because the pixels are too small to see, but because the very concept of a point has been replaced by something richer and more uncertain. This fuzziness is another powerful mathematical argument for a pixelated cosmos, where the smooth, continuous stage of classical physics dissolves into a quantum tapestry of interwoven, non-local relationships. This strange quantum blurring forces us to confront the most enduring mystery of the small scale. A particle like an electron does not exist in one place at one time until we observe it. It is a ghostly cloud of possibilities, a wave function describing where it might be found. Then, in the instant of a measurement, that cloud of maybe collapses into a single, definite point. The electron is suddenly just here, but what, in a universe without a conscious observer, actually triggers this collapse? If spacetime itself is a tapestry of discrete quantum grains, this measurement problem takes on a completely new form. What does it even mean to measure a position in a world built from finite pixels? The very idea of an exact location becomes an approximation, a large-scale average over the fundamental grains of the spin network. The measurement is no longer a mysterious act that conjures reality from possibility. It is a physical interaction, a specific event where the quantum system you are measuring becomes entangled with the quantum state of spacetime itself. The act of measurement selects one particular configuration from the myriad possibilities of the underlying spin network, locking it into place. The wave function's collapse is not a magical event, but a concrete, physical rearrangement of the spacetime quanta, a domino effect that ripples through the fabric of reality to establish a definite here and now. This perspective grounds the most ethereal of quantum puzzles in the tangible dynamics of a pixelated cosmos, suggesting that the universe does not need an observer to make it real, only the constant, relentless interactions of its own fundamental pieces. That single point of infinite density at the beginning of time is the most glaring signal that our physics is incomplete. The Big Bang singularity is not a place or a moment we can describe with our current laws. It is the point where those laws simply give up and surrender. The equations of general relativity break down completely, predicting a state of infinite density and temperature that is more a mathematical cry for help than a physical description. But a universe built from finite pixels offers a stunning escape from this logical dead end. You cannot compress the entire cosmos into a volume smaller than the fundamental quantum of space itself. There is a final, indivisible box, and reality cannot be squeezed any smaller. This fundamental graininess introduces a powerful cosmic repulsion, a force born from the quantum nature of gravity itself that pushes back against total collapse. In this new picture, the Big Bang was not the absolute beginning of everything. It was a turning point, a monumental rebound from a previous cosmic era. Our universe, in its fiery infancy, may have been born from the death of another. This is the concept of a big bounce. Imagine the previous cosmic cycle as a vast universe contracting under its own gravity, growing hotter and denser as all matter and energy converge. Instead of crushing itself into a meaningless singularity, the universe compresses only to the smallest possible volume allowed by its pixelated structure. At that ultimate moment of density, the quantum repulsive force becomes overwhelmingly powerful, like a spring compressed to its absolute limit. It triggers a vast, explosive rebound, a new expansion that we now call the Big Bang. This cyclical model, directly derived from the equations of loop quantum gravity, suggests a cosmos without a true beginning or end, an endless rhythm of contraction and expansion. The discrete structure of spacetime itself acts as a cosmic trampoline, ensuring that the universe can never truly destroy itself, only transform. So the question of what happened before the Big Bang receives a profound answer. There was a before, there was another phase of the universe, perhaps very different from our own, whose final collapse gave birth to our entire cosmic story. Our quest to see these pixels of reality faces a wall of technological impossibility, at least for now. The Planck scale is so profoundly small that building a machine to probe it directly would require an accelerator larger than our entire solar system, a project far beyond any foreseeable future. Yet the history of science is a story of impossible dreams becoming mundane reality. We once thought the atom was the final frontier, and then we split it. Today, new generations of experiments are being conceived, blueprints for far future observatories that will listen for the universe's quietest whispers. One audacious concept involves transforming our solar system itself into a single, gigantic instrument. Imagine a fleet of spacecraft, each housing ultra-precise lasers, positioned across the orbits of Jupiter or even Neptune. This would create a gravitational wave interferometer with arms millions of kilometers long, sensitive enough to detect the faint quantum jitter of spacetime foam imprinted on the ripples from the earliest moments of the Big Bang. Another approach looks to the oldest light in existence, the cosmic microwave background. This afterglow from the universe's infancy has traveled for over 13 billion years, and its journey may have been subtly scrambled by the granular texture of space. The faintest patterns of polarization in this ancient radiation could hold the fossilized imprint of the universe's pixelated structure, a cosmic signature waiting for a telescope powerful enough to read it. But the ultimate breakthrough will not come from a single observation. It will arrive with a complete theory of quantum gravity itself. Unlocking the fundamental code of spacetime would be more than a philosophical triumph. It would be a technological revolution. We would move from being passive observers of the cosmos to becoming active participants in its geometry. The energy of the quantum vacuum, that seething ocean of potentiality, could theoretically be tapped, offering a power source drawn from the fabric of nothingness itself. The manipulation of spacetime topology, the ability to stabilize the transient wormholes in the quantum foam, would rewrite the laws of physics as we know them, rendering vast interstellar distances meaningless. These are not mere fantasies, but logical consequences of a theory that truly unites the quantum and the gravitational. The philosophical mystery of a pixelated reality would suddenly become the most practical engineering manual, turning the deepest questions of existence into the bedrock of a new civilization. This granular foundation might not be unique to our cosmic home. If our universe is built from finite pixels, then any other universe existing alongside it in a vast multiverse would likely share the same fundamental discrete nature. The pixel itself could be a universal constant, but its size might not be. Picture a cosmic artisan able to weave tapestries from threads of different thicknesses. One tapestry might have a coarse, visible grain, while another is so fine it appears perfectly smooth to any beings living within it. This is the vision offered by the landscape of string theory, a vast theoretical terrain of possible vacuum states. Each stable valley in this landscape represents a different possible universe, with its own unique set of physical laws, forces, and even number of spatial dimensions. All of these wildly different realities would not be built from different substances, but from different configurations of the same underlying quantum building blocks. Our universe, with its 3 dimensions of space and its specific strengths for gravity and electromagnetism, would be just one possible arrangement. Its particular resolution, the precise size of its spacetime pixel, would be a single setting on a cosmic menu of possibilities. In another universe, the pixel might be larger, making the graininess of reality apparent at the scale of atoms, fundamentally altering chemistry and life. In another, it might be so infinitesimally small that the illusion of continuity is virtually unbreakable. This transforms our understanding of the laws of physics. They are not absolute, eternal commandments. They are more like local bylaws, emergent properties that depend entirely on how the quantum threads of that specific cosmos are knotted together. The very dimensionality of space could be a contingent fact, a fortunate roll of the cosmic dice that gave us a stable, 3-dimensional stage instead of a chaotic, higher-dimensional soup. So the seamless reality we take for granted might be more than just an illusion. It might be a local custom, one specific expression of a deeper, digital truth that weaves countless worlds into existence. Speculation, no matter how elegant, must ultimately face the cold, hard light of data. The beautiful vision of a pixelated cosmos remains just that, a vision, still awaiting the crucial experimental confirmation that would elevate it from a compelling idea to a law of nature. A healthy skepticism is not just welcome in this pursuit, it is essential. The scientific method is not a path to comfortable truths, but a rigorous, self-correcting process that demands we follow the evidence, even when it leads away from our most cherished theories. For every physicist captivated by the elegance of loop quantum gravity or the holographic principle, there are others who point to significant and unresolved challenges. The most prominent of these is the threat to Lorentz invariance, that sacred symmetry underpinning Einstein's relativity. If spacetime has a fundamental grain, a built-in grid, then it could provide a preferred frame of reference, a cosmic North Star for motion. This would mean the speed of light might vary imperceptibly for particles of different energies moving in different directions, a violation of a principle that has been verified with exquisite precision. Critics argue that introducing this kind of discreteness creates more problems than it solves, potentially dismantling the very framework that makes our universe consistent and predictable for all observers. The drive to resolve this tension is not a weakness of the theory, but the very engine of scientific progress. It forces proponents to refine their mathematics, to search for loopholes, or to predict subtle, second-order effects that could be detected. This is why we build gamma-ray telescopes to hunt for those delayed photons from across the universe, and why we cool atoms to near absolute zero to watch for a jitter in the ticking of time itself. These experiments are not just tests of a single idea, they are a testament to the integrity of the scientific process itself. A theory that cannot be tested is merely a philosophy, a story we tell ourselves about the universe. The great promise of the pixelated universe is that it makes concrete, falsifiable predictions. It lays its cards on the table and dares reality to prove it wrong. This ongoing dialogue between bold speculation and meticulous verification is what separates a passing fancy from a profound truth. The ultimate judge will not be the elegance of the equations, but the silent, unambiguous testimony of the cosmos. The convergence of these distinct paths is impossible to ignore. Loop quantum gravity weaves space from threads, the holographic principle projects it from a cosmic screen, and causal set theory builds it from pure sequence. Each begins with a different set of mathematical principles, a different starting philosophy for what reality could be. Yet, as they journey deeper, they all arrive at the same startling destination, a universe that is fundamentally granular. This is not a single theory shouting in the wilderness. It is a chorus of independent voices harmonizing on a single, radical note. When such diverse mathematical landscapes all yield the same foundational feature, it stops feeling like a coincidence and starts feeling like a clue. The pixelation of spacetime appears less as a speculative idea and more as an inevitable conclusion, a necessary ingredient for any coherent description of nature. This convergence gives the hypothesis its profound weight. It resolves the most catastrophic failures of classical physics, those points of infinite density that signal a complete breakdown of our understanding. By introducing a smallest possible volume, a final pixel of reality, the math simply cannot produce a true singularity. The infinite is banished, replaced by a state of extreme but finite density. The same granularity offers a plausible escape from the cosmological constant problem, that staggering mismatch between the predicted and observed energy of empty space. A finite universe with a finite number of pixels can only contain a finite amount of vacuum energy, naturally imposing a ceiling that smooth, infinitely divisible space could never provide. The most elegant thread weaving through these theories is the deep, unexpected link between quantum entanglement and the geometry of spacetime itself. The very distance between 2 points seems to be a measure of their quantum connection. This suggests that the solidity of space is not a primary substance, but an emergent property of a deeper network of informational relationships. We are left with a compelling, if still incomplete, portrait of reality. The seamless continuum of our daily experience is a magnificent and necessary illusion, a high-resolution projection that hides a more fundamental, digital truth. The final theory of quantum gravity will not choose one of these paths, but likely synthesize their deepest insights into a new, unified language. The evidence is building that to finally understand the cosmos, we must accept that its beautiful, smooth canvas is at its heart a breathtaking quantum mosaic. This journey into the pixelated heart of reality is at its core a deeply human one. Our intuition is a magnificent tool, perfectly calibrated for survival in a world of medium-sized objects moving at moderate speeds. We instinctively understand a rolling ball, a flowing river, a solid wall, because our senses and our brains evolved to navigate this middle world. Yet this very strength becomes our greatest weakness when we try to grasp the universe's fundamental nature. Our gut feeling insists that space and time are smooth and continuous because on our scale they appear to be. We are like fish who have never known anything but water, instinctively believing their liquid world to be the only possible state of existence, completely unaware of the strange, gaseous atmosphere above. The revelation that reality might be granular at its foundation is a profound humiliation of our innate senses. It demonstrates that our most basic experiences, the feeling of a solid floor or the uninterrupted flow of time, are a kind of convenient lie, a low-resolution user interface that hides a far more complex and alien operating system. This is not a demotion of our place in the cosmos, but an elevation of its wonder. It connects the fate of a single thought in your mind directly to the quantum vibrations of space-time itself. Every decision you make, every memory you form, is a process unfolding on this fundamental computational fabric. You are not just a passive observer of a pre-recorded cosmic film. You are a conscious, information-processing node within an actively computing universe. The very act of you questioning this reality is the universe's code becoming aware of itself, a local region of the network reflecting upon its own structure. This transforms our quest from a cold, abstract calculation into a personal exploration. We are not just trying to solve an equation, we are trying to read our own source code, to understand the rules of the game we are all immersed in. The search for the universe's pixels is the ultimate act of self-discovery, a reminder that the strangeness of the quantum world is not distant and separate, but is the very ground upon which we stand and the very fabric from which our consciousness is woven. The universe is not just stranger than we imagine, it is stranger than we can imagine. Our journey through the quantum nature of reality suggests a cosmos that is fundamentally pixelated, a digital tapestry woven from the finite atoms of space and time. We have seen how this single, elegant idea resolves the most catastrophic failures of our old physics, taming the infinities at the heart of black holes and offering a plausible escape from the staggering mismatch of the cosmological constant. We have charted the course for future experiments, from space-based gravitational wave observatories to ultra-precise atomic clocks, all hunting for the faintest whisper of this granular structure. This is far more than a simple upgrade to our equations. It is a complete paradigm shift in how we perceive existence. The solid stage upon which our lives play out is revealed as a magnificent and necessary illusion, a high-resolution projection from a fundamentally discrete source code. As we stand on the precipice of potentially discovering the true fabric of the cosmos, the words of the physicist John Archibald Wheeler echo with profound weight. From bit, he proposed that every particle, every force field, even the fabric of spacetime itself, derives its function, its meaning, its very existence from the answers to yes or no questions, from bits of information. The universe may ultimately be made not of substance but of data. We are left to wonder what this means for our own place within this cosmic computation. Share your thoughts on this mind-bending concept in the comments below, and subscribe for more journeys to the very edge of understanding.